Hey guys, I'm Kim Emerson,
Hi, and I'm Katie Hardister. We are the Irrational Duo.
and this is our Team Teach number 2, and we're going to go over Chapter 9, Geometric Figures. All right, let's start by asking Katie, what are corresponding angles?
All right, Kim. So corresponding angles are going to be angles that share the same angle and the same measurement. So we see here that 2 and 6, they are the same angle. They at least appear to be the same angle and the same measurement. So we could, in class, we could have students, take a protractor and, on paper and have them look and see if they are the same angle
I
and share the same
definitely agree
measurement.
with that. And I love that that is color coded so we can see what exactly is the same measure,
Absolutely.
same angle.
Yeah. So this was actually a question from our homework,
Mhm.
and I included it because I wanted to show that even if we were to give students or even ourselves have just a list here of the angles, but
Mhm.
it's not quite labeled. So for our scenario, we had to, of course, know the measurement and then find the angles for this. And then from that, we can see what's corresponding. So the one that catches my eye is this acute angle here, which is 7 and 12. They are both acute angles.
Mhm.
And I see here that 7 and where's my 12? There it is. 7 and 12 are each share the angle of 56 degrees.
So that's
And
how we know they're corresponding.
absolutely. Yeah. And then I see that, of course, the 8 and 11 are obtuse angles, so
Mhm.
they would be corresponding as well. Here is 11, just kind of a way to check
Yeah,
ourselves. So we
definitely.
go to 11, and then we can go to 8, and we see that they're both 124 degrees. So we know that 7 and 12 are corresponding, and 8 and 11 are corresponding.
I have a question.
Yeah.
How could you, like in a classroom, how could you explain what acute and obtuse angles are to like your students?
Well, whenever I was in school, I had this crazy teacher that she would do this silly thing. So I'm going to do it. And it's always stuck with me
Mhm.
that she said acute angles. She would take her hands and she would say, whenever you look at a baby or you look at something cute, you'd go, oh, isn't that so cute? It's a
Yeah.
cute little baby, or it's a cute little. And so we know that this angle is going to be acute.
Yes.
And then she would say, she would make her hands. I can't quite do it. My wrists aren't that bendy, but making it's this way obtuse when you go obtuse, and I don't know what the scenario was that she gave when
Yeah.
she said obtuse, but it's always just stuck with me that it's acute and obtuse. It's just always stuck.
And I
So
find
that's
it the
something
same
that
way. See, I just think it's awesome to see how, other teachers like visually represent these things because,
mhm,
she would just explain, thinking of a cute angle of a little small angle and think about
mhm,
obtuse angle, again, like it opens up. So like the O
mhm,
for obtuse means it's open, acute means
mhm,
closed. So
mhm,
I just wanted to
absolutely.
know. I thought that was a good question.
Yeah, I think that, students, whenever they're young, they definitely, things that are silly and crazy and out there, of course, to other adults, we might look like really actually crazy, but if it sticks with a child, even just one
Doesn't
child, it's
matter.
completely worth it.
Does not
So,
matter. It's the way you teach it and the way you learn. So,
absolutely.
all
All
right.
right, so let's look at the next question. Oh, let me clear my annotations.
You're
There
fine.
we go. So we know, of course, what the acute is, and we know what the obtuse is. But how do you find the measurements of an angle, Kim?
Well, I'll get to exactly how to find it step by step, but like you just said, you just showed us how to find the obtuse angle and the acute angle. And like you said, that's visual. You can visually see that.
Mm-hmm.
So these other angles, you can also see like a right angle, which is literally whenever you could draw a square coming off of that
Mm-hmm.
angle, that's 90 degrees. We have a straight angle, which we should already know because we've been doing this in our homework. We were, teaching about this. A straight
Mm-hmm.
angle is the angle that is exactly 180 degrees. So that's like basically like a line segment going all the way across. That's what makes it a straight angle, 180 degrees.
Mm-hmm.
If it was acute, it'd be 45, or obtuse, it'd be 130, or right, 90.
Mm-hmm.
And then we also have like a reflex angle, which is in between a straight line, 180, and a full angle, which I just think of a circle. So,
Mhm.
and that's 225 typically, but it could be any
Mhm.
angle between 180 and 360. And we should
Okay.
also know what a full angle is. Sorry, we should also know what a full angle is, because that's just, a whole circle. It's 360 degrees all the way around. So
Absolutely.
let's take a
I
look.
was just thinking on that slide
Hmm.
that it would be a super fun way to kind of incorporate. I love getting students up and out of their
Yeah.
seats. I just think it kind of gets the blood flowing and doesn't make them feel like they're caged animals.
Yeah.
That it would be fun to go around the room or even, go around the school
Hmm.
and find where do we see label,
Oh, that's
like with
awesome.
blue, like
Yeah.
painter's tape, like
Yeah.
let's find the right angles, so like walking down, I mean, on the school,
Mhm.
floor, the tile, or like on a piece of paper,
Oh,
we see,
definitely.
of
That's a great
course,
idea.
just like I love incorporating, different subjects
Mhm.
together,
Yeah.
just like an everyday, and I feel like it really reinstates it for the
Mhm.
child and helps them learn. So just kind of taking
Yeah,
this
definitely.
concept and moving it around and just
Yeah.
bringing it up like in other places, everyday places. I think that's great.
I do too.
So,
And looking at this chart right here, it just makes, I love like games. You could find a matching game out of this, because even just looking at the shape of the angle, you should know
mhm,
what these angles are, because they're not going to end up being the same degrees. You know what I mean?
uh-huh,
Because there's a certain degrees for certain ones. And like you
mhm,
said, you can take a protractor, figure out the measurement of the angle, and then you could label whether it's an acute, right, obtuse,
mhm,
right angle, you know what I mean?
absolutely,
Which, even though some are more clear than the others, you could, like, an obtuse angle looks almost like a reflex angle. It's just a reflex angle is bigger. You see what I'm saying?
absolutely,
Like, I definitely think I love where you were going with that.
absolutely.
But
So, can you
what
show us how to find the missing angle here?
yes, ma'am. So let's look at this. So we see that we have this line down here, right? We see that.
Mhm,
Well, we know that's a straight line. So,
mhm,
and this doesn't, like, that would be totally different degrees, but we're not looking for that. We're looking for inside this line. So we
mhm,
know that our line should equal to 180 degrees, correct?
yes,
So one way we could do this is always take the information that is given to you. And that's what I like always try to like refer back to what's given to me, and then try to solve for everything. Don't just try to solve, because there's no way. There's just no way. So you could do this multiple ways. You could do 180 minus 64 and minus 45, and then that would give us 71.
mhm,
And I feel like you could either do that, which is, pretty simple, because we know it has to equal 180, right?
mhm,
Or you can take 64 degrees plus 45 degrees plus what will give us 180. Well, since we already solved for it and we see that it's 71 degrees, let's put that in there and add it together. So, I would have the kids check their work by doing this. You know what I mean? Leaving that blank, and, make sure, take your calculator or use math in your head, solve that for it. And then, in fact, that does give us 71 degrees. So, and that, that's not very difficult. And I feel like, there's just many ways you could do that. You can do subtraction, addition, you know,
mhm,
that's one way to do it.
absolutely.
So now that we, talked a little bit about that, let's move towards complementary and supplementary angles. Could you define those for us?
Absolutely. So the description for a complementary angle
Mhm.
is an angle that adds up to be 90 degrees.
Ooh, and I know
Um,
what that angle is. We just talked about
yeah, what angle is that?
it's a right angle.
Absolutely. So, and then a supplementary angle would be an angle that adds up to be 180 degrees.
Yeah,
So that is going to be our,
line angle.
yes, absolutely. So, to find these, something we could do, the reversal of what you just
Mhm.
did is we could add, of course, the number 52 and
Yeah,
38. And I bet you if we added those up, we would get
that's
90
90
degrees.
degrees.
And the same thing for 128 and
Mhm.
52. I'm sure that if we added those up, you'd get 180
For
degrees.
sure, for sure.
So just knowing, or if you don't quite know just by looking visually, then you know, knowing the degree of the
Yeah.
angle, you know, you could
Well,
definitely
and I
solve it
feel
that
like,
way.
the supplementary angles are a little bit confusing because I see both an obtuse angle and an acute angle there, but you just have
Yes.
to, I feel like a good thing to always tell your student, if you see that line go through both of those angles, and it's not just
Yes.
that, that's an acute angle, be like,
Mm-hmm.
that's an obtuse angle, but that line
Mm-hmm.
underneath changes it. It definitely
It
changes,
does.
like, what angle
Mm-hmm.
it is. And I feel like you just have to, like, make sure that is clear and that is known because you could be trying to label 2 different angles there when there's only one, you know
Yes.
what I mean?
Yes.
So
Absolutely. I agree.
oh,
So, oh, sorry. I keep
fine.
forgetting that I have to clear those. Go ahead.
You're fine.
So now that we know how to find or identify a complementary and
Mhm.
supplementary angle, I know you touched on it a little bit, but can you elaborate some more,
Oh,
Kim? How do you find the complementary and supplementary angles?
so we kind of just went over it.
Hmm.
We take the degrees that we're given, and then we subtract it by what kind of angle it is. So, like you said, supplementary angle adds up to be 180 degrees. So you'll subtract what you're given. So
Hmm.
let's just write down 180. So that's what it's supposed to equal. And then we're given 43 degrees right here. And this is
Hmm.
kind of like a word problem example, and that's a good way. I feel like that's also a good way to do it. Like, here's the answer down there.
Hmm.
But if you were just given determine the supplement, what I
Hmm.
mean, from the angle. If they knew this angle ended up to equal 180 and they were given 43 degrees, they should be able to do that, by themselves. So we take
Absolutely.
180 subtracted by 43 degrees because that's what we're given, and we would get 137. So that means this angle right here is 137 degrees. And like you said, Katie, definitely if we were to add both of those together, we'd get
Hmm.
180 degrees. Even though those are
Hmm.
two different angles, the whole line in general is 180 degrees. So
Absolutely.
the supplement of 43 is 137. And
Hmm.
then we do the same thing right here. Can you tell me what kind of angle this is before we even look at the
I would
problem?
say that that's a right angle, and I'd
Definitely.
also argue that I'm right.
You are right. And definitely, like I said earlier, you could definitely tell that is the right angle, but a good
Hmm.
way to show is to have that box and fill it in.
Hmm.
Because if you can do that, it is 90 degrees. Well, if we know this is supposed to equal 90 degrees, we are going to subtract it by, again, we were given 43 degrees and we're looking for the other one. Subtracted by 43 degrees, same exact steps as the other angles. Nothing changes with this. We would get 47 degrees. And like you said
Okay.
again, if you were to add those two together, you would get 90 degrees.
Hmm. So I have a question though
Oh,
about your illustrations there.
man.
Um, I see that there's arrows on the
Mm-hmm.
ends. What do those mean?
That just mean the line is continuous and it doesn't stop, because if that line didn't have an arrow, that
Hmm.
means it just stopped. But that angle goes on forever.
On and on
That's a
forever.
great question.
Okay,
And that's a good thing, students may not even realize there's arrows on the end of that. That's
absolutely.
what it means. That's what the angles on the bottom right there, 180 degrees. That means that no matter how long that line is, it's still going to be 180 degrees. So
Hmm.
that's a great
Absolutely,
thing.
goes on and on forever. All right, well, thanks, Kim.
So now that we learned a little bit more about that,
Hmm.
let's talk about some concave and convex polygons. Katie, can
Okay.
you tell us what those are?
I sure can.
Okay.
So this is another one that I had. My teacher, whenever I was in elementary, she gave me this crazy scenario, and it's just something that stuck. So whenever you think of a cave, and I see the word cave right here in the word concave. So whenever I think of a cave, and correct me if I'm wrong here, I think of like a bear going into the cave,
Mm-hmm.
hibernation, right? And
Yes.
so she made it really silly that talking about this bear, right? That he's going into a cave. So imagine that this is his cave. Let me draw a little bear.
Yeah.
Sleeping. He's a sleeping bear. That's his head. That's his feet.
Okay.
It's a bear. Okay, that's a bear. Believe me, it's a bear. So the bear has to walk into the cave somewhere. So this could almost be like the opening here,
Yeah, that's awesome.
the
That's
opening for the bear to go in. So a cave goes inward. It has an
caving
opening.
in.
And so if we know we have concave and we know we have convex, if we can identify concave, then we can identify convex. And
Awesome.
it's something that I look at whenever I say concave. I know that cave goes in, right?
Mm-hmm.
But I know here, this arrow, that it goes out, it's convex.
Yes. So like
So,
on concave, right
mhm,
there would be where the angle is going inwards, and then like
mhm,
you said, like right there would be where the angle's going outwards.
outward,
That's a
absolutely.
great visual, and I feel like, just using stories like that, get your students entertained, because
Mhm,
you're telling me you learned this probably in 2nd grade or 3rd grade, whenever you learned it, and it's
uh-huh.
stuck with you. And how old are you?
I'm going to be 24.
Yeah, see, and it's stuck with you throughout the whole time. That's awesome. See, and you'll
Yeah,
never forget it. So I love
absolutely,
that we have stories to tell to explain stuff and make it more visual for our students.
absolutely. So now that we can identify concave and convex, what would you call this shape here, Kim?
I would call that a convex because if you would look down here, you see those little lines are caving
Hmm.
in. Even though, we see that we have some convex in here,
Hmm.
if it caves in at all, it is a concave shape. So, you
Hmm.
know what I mean? So, if it even has
Absolutely.
like, if it only has one piece out of the whole shape caving in, it's a concave. And
Hmm.
if it
So the
doesn't,
bear can enter. If the bear enters
yes,
one time, then that makes it a concave.
yes, ma'am.
Absolutely.
You definitely got
Absolutely.
it.
So moving on to the actual question here. So what is n and what is y? And when solving for an angle that is that has a variable.
Okay. Well, we did this on our homework, and I kind of confused myself because, I'm trying to solve for this, and I was given an equation and everything. So let's look. So we see we were supposed to solve the angles in this shape using this equation, n minus 2 times 180. Well, I didn't know what n was. So if I don't even know what n was, my students wouldn't know what n was. So I thought that was a great question to ask.
Hmm.
So, I learned about it, and I found out that n equals the number of sides our shape has. So let's take a look. So we got 1, 2, 3, 4, 5, 6, 7, 8. And then I actually did that wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or
9
8.
sides.
Sorry. Yeah,
No,
sorry.
9 sides. I was like,
I just started drawing everywhere. Uh,
yeah.
so, I mean, no matter what kind of shape you're given, if you're given a square, what would be in?
N would be 1, 2, 3, 4 sides.
Exactly. So, I mean, and that, if we have a triangle, and would be 3 if we were given.
3.
This is just more of a complex kind of shape
Yeah,
here.
absolutely.
So, but yeah, so that's really all that n is. It's just, the number of sides your shape has, and then you're going to put it
Hmm.
into that equation. So, let's say that we solved that equation and we did 9 minus 2 times 180. Well, and then
Hmm.
we're going to divide and solve for y. Well, so once we get y, we know that y would be 20. But
Hmm.
what does y represent? What does y even tell us? So we know that y, as you can see here, y would be the number. So we would take 20, and you would multiply that by the number in front of it. Because, these two right next to each other is just understood multiplication. It doesn't have
Hmm.
parentheses. It doesn't have a multiplication sign. But if you have a number and a variable standing next to each other, you're supposed to multiply that. So that's just, that's all it is. So you'd have 7 times, 7 times 20.
Hmm.
So, and, you'd have 3 times 20, 12 times 20,
Hmm.
So then it's just an easy way to, I just thought those were good questions, for our students
Yeah.
to like kind of comprehend.
So if you were given this question
Mm-hmm.
and you said 20, 20
Yeah.
wouldn't be the answer then.
No, no, no. You want
That
to
was only
know
like halfway through the problem.
exactly. So you're going to want to take 20, and sub that 20 in. So
Hmm.
it's kind of a long process to like find each angle. But
Hmm.
honestly, you have 3 of the same angles. So you have 7 3 times, you have 3 3 times, and you have 12 twice. So you'd
Hmm.
only have to solve for it once, and then you know it from there. You know what I mean? You wouldn't have to do
Absolutely.
it over and over. So it seems like it would be long and complicated, but it's actually
Just take it step by step.
yeah. So let's take a look. So now that we talked a little bit more about concave and complex and, solving for the angles and why, what are
Hmm.
our interior, exterior, and central angles, Katie?
So identifying these things, when I did this problem, I thought, well, central. To me, central is the middle. It's right in the middle. It seems like any town you go to, there's always like a Central Avenue. Y'all know our Central Avenue. Stay off of it. It's racetrack season. But Central is right in the middle. So to me, I said right here that I would label this the central point. So at that point, I would encourage, that's one of our options gone. Let's cross it off. So then we have interior and exterior. So interior, in is the inside of the house. Exterior is the outside of the house, right? And that even says it right here. In is interior. So
to you right there.
Yeah, it tells you. Absolutely.
In the question. If you think of interior, it's inside. So like, our students may not think of that. Think of that this way. I thought of, interior, inside of my car. The interior is inside of my car. The exterior would be the outside of my car, like windshield wipers, stuff like that. So
absolutely.
Absolutely. Just trying to think of it, on a day-to-day basis, just think of that kind of stuff.
Just making it relatable. Of course, we as adults, that's how I related it. But I think what makes a teacher a good teacher is being able to, whatever your teaching style is. So for me, I definitely like to, like we talked about, make things relatable to students. So you have to think like a student.
But they would want to know what's happening. They want to know why, they want to understand it. They just don't want to be given something and think it's important when it's really not to them. They don't, that's not
absolutely.
That's not on their, forever list. But like,
of course,
like that bear story, that you will never forget that. It's something about it. Just thinking about it, being able
absolutely.
to them.
Just giving students value.
Exactly.
And what they're learning, making it relatable gives them the value. Absolutely. So now that we know the interior, exterior, and central angles, Kim, do you find those angles the same way?
So, when we're finding angles, we do have different ways to solve for them, like that equals 180, the 360, the 90 degree. You could solve that way. This is a little bit different because we're looking for specific angles. But if you think of it that way, angles change. So the answer would be no. You'd have to, you solve them in the same way. But it's not all, you know what I mean? You just don't solve them the same way for all three of them.
Absolutely.
So let's look at interior angles. So interior angles, the inside of the angles, we know the inside would be 180 degrees. So for one angle, of course, for a line. So we would take our n, which we know what n is. Do you remember what n is?
N was the number of sides.
Of course. So we take how many sides we have. So subtract it by 2, multiply it. The parentheses there is understood multiplication. So multiply it by 180 and divide it by n again. And then that will give you our degrees of interior angles. And that never changes either. So like I said about, angles change. To find the angles, not so much, but angles do change. Does that make sense? Am I explaining that?
It does. Yes, it does.
So let's think about central angles. This is, one of our homework problems, the one you just demonstrated. Central is in the middle. So we're going to do you remember how to find, what is a circle equal to be? It's not 180, but it's
360.
Yes, ma'am. So we'll take 360 divided by n, which is the number of sides we have. Well, n would be 9 here. So we do 360 divided by n would give us 40 degrees. So our central angle in the middle right there is 40 degrees.
Okay.
It's pretty easy. I mean, let's look at exterior angles. And exterior angles are a little bit more complicated to me, but not so much like frustrating, It takes a little time to understand. So exterior angles are our outside angles, and we know that this angle right here is 140 degrees. It has nothing to do with that line, but if we were to take 180 minus 40, 180 minus, let me go back. 180 minus 40 would give us 140 degrees right here, correct?
It does.
So we need to take 180 to find the outside. This is a line, so our line equals up to be 180. We remember that from previously. So we'll take 180, subtract it minus 140 since we know what this angle is, and then that will give us 40 degrees. So our angle right there is 40 degrees. Sorry about that. So yeah, like I said, I mean, each one has a certain way to solve for them. Those do not change, but that, what the angle's number is does change.
Absolutely.
So I have a big question. So since we were talking about angles and shapes and everything like that, can a tetrahedron face overlap a cube face? So like in this image.
So in this image here, to clarify, the blue here is a cube, a box, and then the tetrahedron is the pyramid shape there that is in the box. So first of all, the way that I think about it is, think if you have, a pyramid, a small tiny pyramid, and you're going to put it into a gift box, and you have to put it in there just so, and you put it in this way, and it fits in there, but you can't close the lid on the box, so that means it wouldn't fit. So this is the angle that you would have to put it in there at for it to fit in the box close, the gift box close. So the answer would be no, because the tetrahedron in the cube has none of the faces and the planes of the face. And then no, because the tetrahedron in the cube has none of its faces in the planes of the faces of the cube. Boy, that's a mouthful.
And I told us about planes earlier. So like planes are just flat surfaces. So none of its surfaces are touching the cube surfaces. Is that what you're saying?
Yes.
Okay, awesome. That's a great understanding of it.
Yes. Sorry. I should have phrased my wording a little bit better.
No, you're fine.
It's a mouthful.
That is a mouthful. So I see what you're saying. So you're saying that none of the tetrahedron's flat surfaces is touching the square's flat surfaces.
Absolutely.
Awesome. So the way that angle is, where is the top of the tetrahedron if we're talking about a pyramid? Is it where D is? That's where I visually see it.
So it would be right here. We see that this little dotted line here. Yeah. It is the tetrahedron. It has, forgive my drawing, it has a square base.
Oh, yes.
So then you see that you have the triangle, and these triangles are not going to be perfect, but
no,
bear with me. So a triangle. Woo. We're trying. Okay, so the triangle. So we see this is the square base, and then if we took all of those and we folded them all together, then this would be the point right here. So we had to kind of put the bottom up for it to fit in this box.
I definitely see that. I love that you made that visual representation because it's actually showing me how a tetrahedron looks unfolded, and it makes more sense to see like the tetrahedron, the pyramid, close.
Yeah, laid out flat. If you were to lay it out completely flat, then that's what it would look like.
I feel like if you were to see this, a triangle, you wouldn't realize, that the base is a square, you know what I mean? So I feel like having a representation, students could see that, definitely.
Absolutely. All right. So, what is a plane whenever we're working with shapes, though?
So, like I previously just told us, a plane is just a flat surface. So, we've seen that so well in your image earlier. I mean, that's a great visual representation.
Thank
you. And there's different kinds of planes. As you see in this image, we can just think of plane equals flat. So, if we have a shape that does not have a flat surface, it is not, it doesn't have a plane. So, like, let's look at this charger. It's the shape of a cube. So it does have a plane, but if I take this pen, this marker, it does not, because none of it's flat. None of
rounded.
It's exactly. It's rounded. It's rounded all the way. So it does not have a plane, but this cube does have a plane. Sorry, I was grabbing stuff off of.
No, I think that's great. I would say a challenge of making these videos online is that sometimes it's just easier to explain, with a manipulative in the hand. And even as an adult, sometimes it's hard to grasp things without just like putting your hands on it. So I couldn't imagine doing this for a child.
No, and I definitely feel like in a classroom you could have shapes to show, you could have a circle and just be like, does this have a plane? You know what I mean? Be like, no, because it's circular. It doesn't have a flat surface. You know what I mean?
Absolutely.
So, I mean, and we have a geometric plane. You also see that's flat and it has its lines going all the way through it, right? But the plane surfaces, that's definitely a plane because it's flat all the way through. But that doesn't mean the side here doesn't have a plane, because it does. It's flat. The side here, the bottom of it, So let's look at this one. So now that we know what like planes are, let's go into like a little bit more depth to it, while we're talking about shapes and all that kind of stuff. So a plane of symmetry basically divides the shape into two identical parts. So we have a rectangle there, right? If we were to take to do a plane of symmetry and divide that in half, we would have two squares after that. Put them together, we have a rectangle. Apart, two squares. So, and you see how those are identical. They look the exact same. And then when we have this, triangle here, if you were to divide it in half, not like in the middle, but in half, you would still have a triangle. You know what I mean? And even if you were to divide it in half, you'd still have a triangle. And I love this visual representation of the cube, the square. If you were, to take, to find the plane of symmetry there, you would have two triangles. And then just to see that visually, have a triangle here, triangle there, and then make it a square is great. It's how you find like the plane of symmetry as well. Absolutely. But again, could a circle have a plane of symmetry? No. It's not, all of these shapes here have flat surfaces, flat surface there, flat surface there. So, again, if my pen was divided in half, it would not look the same,
Absolutely. Or be usable, I think.
Yeah. So while we're talking about shapes and planes and all that kind of stuff, which is the tetrahedron, the octahedron, and the icosahedron?
And these, okay.
Yes, icosahedron. I say
that. Icosahedron. Yes, that's how you say it. I Googled it. It's icosahedron.
Icosahedron.
I think I'm saying it with, we're from Arkansas, so we're saying it with some twang, but it's icosahedron. Whatever, we're going with it.
We're good. Okay. We're good. We got it.
We got it. Okay, so for me, the first one that I see, and again, whenever we are, anytime that I'm given any kind of list and have to decide which is which, I'm immediately going to write down the facts. What do I know for a fact? So whenever you asked me this question, the first thing that I saw was right here where it says octahedron. Octa, when I think of octa, I think of an octopus with 8 legs, right? Octopus, unless he has a deformity, which in case we do love octopus the same, but 8-leg octopus. So with that, I'm going to take that information that I know, and this one here I laid out flat for us, and really I could have done that for each of them, but I just really liked this visual. So we awesome. Can take this information and take it with our next. So with this, I see that it has 1, 2, 3, 4, 5, 6, 7, 8 faces. Yes. So there's 8 flat surfaced faces. And if we fold them all together origami style, then we know that we would come up with an octahedron. Ooh, so this one is going to be the
I love the, you saying octahedron, the octopus has 8 legs. See, that kind of stuff gets your students entertained, like the bear thing. You will not forget that. You cannot forget that.
Absolutely.
The octopus, 8 legs.
So then we know that we've already used the octahedron. So we're done with that one. Cross it off. We're done with it. So now we only have 2. So we're going to use process of elimination to decide which one is which. So a tetrahedron, we saw a couple problems back. Yes. That the pyramid that I drew. Remember, I had a square base and it had 4 faces that laid flat. And whenever I put them together, they formed a pyramid. also known as
A
a tetrahedron.
tetrahedron. That's awesome. Where you visually drew out the square and then the four sides unfolded, basically, is what you did earlier. Awesome.
So
now
the tetrahedron and octahedron are taken up. And I'm just going to let you know this because I'm going to say I didn't know this. Now, this is the prettiest shape of them all to me, but also the hardest to say and the one with the most faces.
Yeah.
Can you guess how many faces are in this isohedron? Isohedron?
I am not sure. Hang on. Let me think.
Well, I'm not going to let you count because I'm going to tell you.
Okay.
It's 20 faces. 20 faces in that. That's a lot. Could you imagine having to origami fold all of that up? It would take forever.
Oh my gosh. I couldn't imagine seeing a shape that had 20 faces.
Yes. I don't know where you would actually see this in real life.
I don't know.
Gallery.
You'd have to.
Yeah. So it would be kind of hard to make that relatable to students where you would see that at. Maybe like I would use like diamonds or something, maybe. I don't know. But, that's my shapes there.
Yeah.
I would, in class, if I was in a real class, I would definitely maybe speak with my art teacher and see if we can work together to maybe have her come help me because I for sure can't do it.
Yeah.
But I would try, but I'd probably fail.
Well, I was in a geometry class when I was doing some basically observing, from one of my other classes, previous class. He had the actual shapes in a container where the shape was, but if you took it out of the container, you could unfold it, and he had them count the sides, count the edges, count the vertices.
Oh, really?
Yes, it was awesome. He had to explain to them how to open it because he had to pull up and then it would unfold. But I'm telling you, they have so much stuff in the classroom. It's so beautiful and hands-on.
What grade was that?
I think it was 6th grade. It was 6th grade. Yeah.
Yeah, that seems about right. 6th grade. That's awesome.
The faces, the edges, the vertices. It was just, it was awesome to watch them be so engaged and actually collaborate and not talk about recess, So
absolutely. Was that a resource that the school gave him, or was it something that he made?
It was the school's resource.
Absolutely. Well, that's awesome, and something that I would love to get my hands on to teach in my classroom. Yeah. Oh, let me clear my.
Oh, you're fine. No, he was very, very, very do not mess these up, people, please. Use them.
Yeah. So, Kim, we've talked about faces. We talked about edges. Well, we haven't talked about edges. I'm sorry. We've talked a little bit about faces, but what are faces, edges, and vertices of a shape, and how do we label them?
Okay, so like what he was doing, so we already know what faces are. They're the surfaces, the flat surfaces on a shape, right? Vertices are where, basically, I'm gonna go ahead and tell you edges. Edges are like the lines in a shape, a straight line in the shape. Whether it's into a square, whether it's in circular, it's a line. It's the lines in the shapes. Well, a vertice is where those two lines meet and make, a point, basically. They make a point, corner, pointy. I just think of wherever there's pointy, it's a vertex. You know what I mean? Yeah. But it's basically just the corners of a shape. Some may have less than others, you know what I mean? But if you have a square, you have more than a triangle, So,
absolutely.
It's just a great way to see it. So I'll do this first one, and then I'll ask your help on the second one. So we already know what faces were. So we're going to guess that our face, looking right here, our face would be right here because this is the visible surface. This is the, you know what I mean? And that could be right here. Yeah, the flat visible surface. It could be right there too. Well, our lines, that's a line, and that's a line. That would be our edge. Our edges, that could also be our edges as well right here. But where those two lines meet right here, that is our vertice. But, right here is a vertice. You see, is that very visual for you? Does that help?
Absolutely.
So you can see where any 2 points meet, you have a vertice, and that would also be a vertice as well. So, do you want to help me with the second one?
Absolutely.
All right.
So the second one to me, it looks like a room, like even like the room I'm in. I
Mm-hmm.
would say that like the walls, the flat walls
Yes.
would be the faces, the surfaces.
You're
So
saying
that one
this would
there.
be a face because you would think
Hmm.
of a room, a person inside of this room. That's the
Yeah.
wall. That's the wall. That's the roof. I mean, that's a great way
Yeah.
to explain it.
Yeah.
So where would you think, where would our lines be?
So our lines, I would say, is like the tops and the sides and the bottoms of each square. So
Oh,
I would say that the edges would be the edge of the walls.
awesome. That's a great
Hmm.
way to say it. So like this right here would be an edge. That would be an edge.
Hmm.
That would also be so anywhere that has like a line to outline the shape has an edge.
Hmm.
So
Hmm.
let's refer back to my cube. So this would be an edge. That would be
Uh-huh.
an edge. Edge,
Yes.
edge, and then this is the surface.
Yes. So then I would say that I would say that the corners or the vertices would be anywhere where those lines or the edges, the straight lines where they meet together.
Oh, right
That
there.
would be a corner or a vertice.
So right there, also known as a
Yes.
corner. So like right here, we know our edges,
Hmm.
our surface, but we know, vertices are where the two edges meet. So right here would be a vertice, right
Hmm.
there would be a vertice,
Absolutely.
vertice. See, I feel like just having shapes, like if we were giving the materials in a classroom, it would be so easy. It would be so fun. You know what I
Yeah,
mean? I just feel like it'd be so visual. But I think
absolutely.
this next one's a little bit more tricky.
So that's a cone, right?
Yes, it is a cone. It's a
Okay.
circular cone.
I'm not sure about that cone. You're going to
Okay.
have to help with that one.
Well, we already know where our vertex is. Anything that points, where the two lines meet. So that would be the top up here. Nothing changes about that. A vertex is a vertex.
Okay.
So, and we still have our surface, like right here in the middle, our surface,
Hmm.
our flat surface. It's still flat, even though it's circular. It's still flat
Hmm.
surface, but we just label it different. So we would just say this is either, you can say a curved surface, you could say a circular surface. You can label it
Round.
however you want. You just can't say it's a surface. You have to label
Okay.
it whether it's flat, curved, circular. But then also, this right here would be our edge. Our line right there. I hope you can see that line right there.
I can.
You cannot? Oh, you
I
can?
can.
Okay,
Yes,
awesome,
I can.
awesome. I was like, oh, no. Our line right there. And then that could be, these lines, that line, you get it. But right here, this would also be that would be our surface, our flat surface. Because this is our circular shape that's on the bottom. So like if you were to
Okay.
set that shape down, it'd be flat. You know what I mean? But
Hmm.
the circular cone going up, it gets smaller. It's not one stable, it's not one stable shape. Otherwise, it would be a rectangle. You know what I mean? If it had this
Absolutely.
shape going up. So I hope that helped. That is the end of our slides, guys.
All right. Well, it's been fun, Kim. Thank you.
You're welcome. We'll see you guys next time.